One of the most important proof techniques in mathematics is induction. When you first learn about it, you will often see fairly simple examples, since they are supposed to help you learn the formal aspects of induction. Therefore, they might not be too interesting in and of themselves, even though some of them are good to have in your problem-solving toolbox. I'm Bernhard Werner, this is Summer Product, and in this video, we will look at a few of these typical examples, solve them with and without induction, and talk a bit about why you have to do them in the first place. Let's start by saying what induction actually is. Many statements in mathematics say that something is true for all natural numbers n. Maybe that the sum of the first n natural numbers is of a specific form. Maybe that a certain expression containing n is always divisible by 64. Maybe that if you have a network of n dots without any loops, you will always have exactly n-1 connections. Maybe that if you take n non-negative numbers, the nth root over the product will always be less than or equal to their sum divided by n. Or that if you cut a pancake with n cuts, you can get a maximum of n squared plus n plus 2 over 2 many pieces. So many results in mathematics are of this particular form. For all natural numbers n, we have statement. It is common to write the statement as P of n when talking about the general structure of proofs by induction. P here stands for proposition, which is basically just a different word for statement. And of n means that the proposition depends on the number n. And as you have seen, the statement can vary quite a bit in its form and complexity. When you want to prove that these are true, you will usually play around with the exact formulation of P of n to see whether you can transform it into something more tangible. Sometimes it might be possible to show that a statement about n is true if only you could show that it is already true for the smaller number n-1. If you write this transformation down in an orderly way, you might be able to use it again and make one more step and relate P of n-1 to the statement about n-2, and then about n-3. This goes on until you arrive at a proposition about the smallest natural number for which it actually works. As with the example statement on screen, this will often be 0, maybe 1, but sometimes it's a statement that only works for numbers bigger than, say, 5, or 20, or 400. If you can then show that this smallest case is true, you can go back up the chain until you arrive at the general number n you started with. What proof by induction now means is to write this process here down in a structured and standardized way, such that it is easier to follow and to see that it is actually correct. Let's look at an example to see how this actually works. For any natural number n bigger or equal than 1, the sum of the first n positive integers will be n times n plus 1 divided by 2. In the vast majority of cases, this will always be the first example you see for induction. To prove it, we begin with the smallest possible number, n equal 1. This is called the base case or base step or something similar. On the left hand side, we want to sum the first n positive integers, but because n is equal to 1, 1 itself is the only number in question. This is often the very first stumbling block when you are new to induction. The base case is usually a very simple edge case that is quite tricky to parse and understand. When you write it down, be very careful. The right-hand side is much easier to evaluate. We plug in the value we have for n and we get the same result as on the left-hand side. Next is the so-called induction assumption. We assume that we already have proven our statement for a certain number n. Then comes the induction step. If we know that the statement holds for n, we want to argue that it also holds for n plus 1. Note that this is written the other way around of how we motivated it at the start of the video. There we reduced the n case to the n-1 case. The argument is the same in the end. If the statement is true for some number, we show that it is true for the next larger number. Here, this means that we have to consider the sum over the first n plus 1 positive integers. The whole point of induction is to use the induction assumption, i.e. to use the knowledge that the statement is true for n itself. In the induction step, you will always have to find the statement from the induction assumption we made before. Here it is quite straightforward. We split the sum into the first n numbers plus the last one. By the induction assumption, we can replace the sum over the first n numbers with the given expression. And then it's just some simple algebra to put everything together. But here is the next common stumbling block. When you use induction to prove formulas like this one here, you have to make sure that the final form in the induction step contains n plus 1 explicitly. We We have to see the n plus 1 at the same places the n from the induction assumption is in. In this example, this is rather simple, but with more complex examples, it might not always be obvious how to get there. In that case, it is sometimes easier to start with the n plus 1 version you want and massage it until you end up with the intermediate result you got earlier. There are no hard and fast rules for how to do this, so just remember, in the end, we have to have n plus 1 as a distinct building block in our expressions. And that is induction. We started with showing that the proposition is true for the smallest possible value. In this case, it was 1. Next, we assumed that it is true for some value n. And from there, we concluded that it must also hold for the next largest number, n plus 1. This allows us to do the iterative process we saw in the beginning. From a solid starting point at 1, go to the next number, and to the next, and to the next, and to the next, on and on and on. When you are learning induction, it is often important that you write it down in this precise way. Base step, assumption, induction step. There are two main reasons for that. First, induction is used in a lot of areas, and it can get tricky to see where the induction step actually happens. Second, many students encounter induction around the same time they are learning about more formal logic, dealing with all sorts of new mathematical symbols and proof techniques, proper reasoning, etc. Both make it very beneficial for the learning process to be overly rigorous, even if you can be more lax later on. Note that for the argument itself, it only matters that you covered the base case and the actual induction step that brings you from one point to the next. In particular, you don't have to do them in the order I presented them. You don't have to write down the induction assumption explicitly. You don't have to name the steps like I did, or name them at all. As long as the logic is solid, the induction proof is fine. But since there's so much going on, many teachers insist on a very particular way to do induction. Learning the formalism is a main goal of all these exercises. In this video, I will make it progressively less formal over time. And the reason you often see the same types of exercises while learning induction is that they are self-contained and overall fairly simple, which is not true for how you usually find induction out in the wild. There are many examples of big and complicated induction proofs. For example, one about Latin squares. A Latin square is an n by n grid which contains the numbers 1 to n exactly once in each row and column. One fairly natural question one could ask is, if you have a partially filled Latin square, can you complete it? One answer is the following. If you have an n by n grid with n-1 entries, such that no number appears twice in a row and column, you can complete the grid to form a Latin square. And the proofs for this are quite long. The induction proof in Proofs from the Book, for example, is about 2 pages of dense text and another page of diagrams. You can't really do that as an exercise, especially not if the main goal is to teach induction itself. Another way induction pops up is as one small step within a long sequence of arguments for a proof. Again, something that's very impractical to use as an exercise, as you would often have to do the non-induction parts, at least up to this point. Lastly, remember that we started with statements of the form, for all natural numbers n, the following is true. It is conceptually quite easy to prove this via induction if I tell you that you can prove it via induction. But not all results of this type can. Probably only very few can. But if the topic of the lesson or exercise sheet is to learn induction, most of the examples should be solvable with induction, which cuts down our options. Obviously, it would be best to have a variety of problems and let you figure out for yourself how to tackle them best. Alas, there's only so much time in any given semester or school year. But you can do that for yourself. For each and every induction exercise you get, you should try to solve it without induction too. In particular, for statements that claim that a certain formula is true, you should try to find the formula yourself, instead of just proving that it is correct. Let's see how that can look like with the sum expression we already saw. This formula was famously used by a young Carl Friedrich Gauss to sum the numbers from 1 to 100. Whether the story about the lazy teacher is even remotely true is doubtful. Nevertheless, we call it the Gauss sum. And the passed down proof for it goes like this. You can take the smallest number, 1, and pair it up with the largest, n. Together they give n plus 1. The second smallest and second largest number together also give n plus 1. We pair up every number with one from the opposite end of the line. We will get n pairs which each sum to n plus 1, so together they give n times n plus 1. But we counted every number twice overall, so we have twice the desired expression. A visual proof, which is the same calculation under the hood, build a triangle from tiles, such that the first row has 1 tile, the second 2 tiles, and so on. Then the total number of tiles in the triangle is the result of the sum we are interested in. Now, duplicate the triangle and assemble both into a rectangle of side lengths n and n plus 1. We now have twice as many tiles as we want, and they form an area of n times n plus 1. Many of the induction exercises you will see have an alternative proof, such as these: rearranging and combining parts in a clever way, or drawing a picture. In the rest of the video, I will show you some of them, and we will compare the two approaches to see where induction is easier. After summing the first n integers, let's see what happens if we sum the first n square numbers. On the induction side, we do just about the same to prove the stated formula. The base case again means to only look at a single summand on the left, which gives 1. And on the right, we also get 1. The assumption then is that the formula on screen holds for n. For the actual induction step, we look at the sum of the first n plus 1 square numbers. As before, we take the first n of them and replace them with the formula from the induction assumption, which should always be your first try with these sum formulas. Then we write everything as a single fraction with the numerator fully expanded. We know that we want to end up with this fraction here, with n plus 1 plugged into the final right-hand side formula. Starting from here, we can expand and go backwards to see that we end up with the same fraction as before. On paper, of course, you might want to actually do that with a few more details, especially in an exam. For an alternative proof, look at this triangular arrangement. We have 1 once, 2 twice, 3 3 times, and so on, until the last line with n copies of n. What's the total sum of the triangle? Well, exactly what I just said. 1 times the 1, plus 2 times the 2, plus 3 times the 3, until n times the n. Exactly the sum of the first n square numbers we want to find a formula for. Now let's take 2 copies of the triangle which are rotated. Instead of filling them with 1 at the top corner and n at the bottom edge, we take each of the other 2 possible arrangements, filling it from bottom left to top right and filling it from bottom right to top left. All 3 triangles together now are 3 times the sum of squares. If you sum up the 3 numbers that sit at the same place within the triangles, you will always get 2n plus 1 at every single position. And how many times does 2n plus 1 appear on the right? Which is the same as to ask, how many entries does such a triangle have? Well, it's 1 entry in the first row, 2 in the second, 3 in the third, on and on and on, until n in the last row. But that's precisely the sum we had in the previous example. So we know that it is equal to n times n plus 1 over 2. Together, that means that the numbers on the right sum to 2n plus 1 times n plus 1 divided by 2. We only have to get the factor of 3 from the left over to the right to find the original claim. Now, are you supposed to find such a proof on your own? No, of course not. First, summation formulas lend themselves to induction quite well anyway. And this proof in particular is quite out there. But when doing lots of math, you will often encounter summation formulas in weird variants, partial sums, or unexpected configurations. The more you play around with them during homework, the easier it will be to recognize them out in the wild. Apart from these sum formulas, you will probably see quite a few statements about divisibility that you are supposed to prove via induction. With this, we enter the realm of number theory, an area where even the simplest looking statements might be incredibly difficult to prove. Even worse, there's a whole box of approaches to any specific problem. So, I'll show you a very simple exercise and a very difficult one, to illustrate the range of complexity that's awaiting you here. To get started, we will prove that n squared plus n is always an even number for n at least 0. We start with induction again. The base step is easy enough. 0 is an even number. The assumption then is that we already know that n squared plus n is even. For the induction step, we look at the expression with n plus 1 in it. The general idea is to expand this and rearrange it such that the n expression from the assumption becomes visible. Here we do that by using the binomial formula on the left. We put everything we see in the assumption together and move everything else to the side. The first part is now even by the induction assumption, and the right is even because it is a multiple of 2. So we are done. For a more direct proof, the shortest argument is probably to say that the square of n is even if n is even, and that it is odd if n is odd. We say n squared and n have the same parity for short. And summing two numbers of the same parity, i.e. two even or two odd numbers, will always result in an even number. Now let's try a more complicated statement that can be solved with the same ideas. I claim that for n at least 0, the expression 3 to the 2n plus 1 plus 40n minus 3 is always divisible by 64. This seems like a lot to take in, but for the induction approach, we know where to start. Plugging in n equal to 0 makes the whole expression 0, just as in the last example. The assumption is that the expression in n really is divisible by 64. For the induction step, we try the same as in the last example, extracting the n expression from the n plus 1 expression. We won't be able to do that as nicely though. We will end up with a multiple of the n expression. But that's fine. Any multiple of something divisible by 64 is itself divisible by 64. And also similar to the example before, we will have a leftover term, but one that's very obviously a multiple of 64. This is usually the strategy you want to go for in proving divisibility rules via induction. Split the expression into something containing the term from the assumption plus something that is easy to deal with. To actually do that here, we look at the power of 3. Splitting it up, we see that we get 9 times the power of 3 we want. That means the multiple a we are looking for is probably 9. So let's try to massage the other terms such that we get 9 times 40n minus 9 times 3. After expanding the other summons, we do have 40n only once, but we want to have it 9 times. We simply write it down 9 times, but then we compensate by subtracting it 8 times. Overall, we have the same 40n from the line above, but we can now use the last summand for our leftovers. For the constant term, we do the same. We want to have minus 9 times 3, so we write it down. To get to the 37 that is actually in our expression, we have to compensate by adding 64. Now we rearrange everything slightly and see that we have the structure we wrote at the top. A multiple of the n expression, which is divisible by 64 by assumption, plus something that is obviously divisible by 64. And we are done. Now let's try to find a proof without induction. When we take the power of 3, we can rewrite it a bit to see that we have a nice clean power of 9 here. We want to analyze divisibility by 64, which is 8 squared. The idea we now want to have is that 9 is just 1 larger than 8, which comes out of nowhere. But if you remember it, it's a very neat trick to tackle this kind of problems in the future. Let me show you how this is helpful. When writing 9 as 1 plus 8 and raising it to the power of n, we can expand this product. Doing so means to multiply every summand in every factor with every summand in the other factors. Concretely, a bunch of 1s get multiplied together with a bunch of 8s. Let's do this systematically. We have a single way to combine only the 1s, and they multiply to 1. Choosing a single 8 and n-1 ones gives us a product of 8. And there are n ways to do that. When we take 2 8s and combine them with n-2 ones, we get 8 squared. There are many ways in which we can choose these 2 8s. But we won't be needing the exact number. Let's just call it k2. Next, we combine 3 8s with n-3 ones to get a multiple of 8 cubed. Again, the exact number of combinations won't be important in a minute, so we call it k3. We continue this. When expanding this product, we get larger and larger powers of 8, and a certain number of how often this particular product appears. If you did this properly, these k numbers we wrote here would be so-called binomial coefficients, and there is a precise formula for them. But all that's relevant to us here is that from the second summand onwards, we have a factor of 8 squared, 64 everywhere, which we can factor out. Let's write this as 64 times capital K for short, where capital K stands for a very complicated expression we don't actually care about. This is why writing 9 as 1 plus 8 works. It allows us to extract a multiple of 64 directly, and the rest, 1 plus 8n, is a very simple term. To finally get back to the expression we are actually interested in, we can replace 9 to the n with what we just computed. And after multiplying it with 3, everything collapses pretty quickly to a multiple of 64. Now, which of these proofs did you find easier? This is certainly a good induction exercise, but induction didn't reveal any deep truth here. But it might be more straightforward. The trick in the non-induction version to write 9 as 1 plus 8 is weird if you have never seen it. But once we dealt with that, the rest of the proof was very simple. And the overall complexity of the calculations we had to do was more or less the same, I would say. Let me know in the comments which proof makes more sense to you here. There's one last type of induction exercise I want to show you in this video, namely recursion. That means we define a sequence of numbers by a start value and then give a rule how we generate new numbers from old ones. Just from this description alone, it reeks of induction. So much, in fact, that induction and recursion are often treated as synonyms. Even the first example we saw in the video can be formulated like this. Let S0 be 0 and say that Sn is given by Sn minus 1 plus n for all larger n. This is just another way of saying that the nth number here is the sum of the first n positive integers. And so you might encounter the exercise to prove that Sn, defined like this, is equal to n times n plus 1 over 2. The induction argument is the same as we have already done at the start of the video, so I won't repeat it here. Instead, I want to go to the poster child of recursive sequences, the Fibonacci numbers. They are defined like this. Let the zeroth and first number both be 1. Then we define every other number in the sequence as the sum of the previous two. There are dozens, if not hundreds, of common properties and identities one can show for this sequence. Here I want to look at only one, namely that for all n at least 1, the 2nth Fibonacci number is the square of the nth Fibonacci number plus the square of the n minus first. Any such property for a recursively defined sequence should be provable via induction. Emphasize on should. Let's give it a try. It will be a bit more obvious what's going on if we start with the induction step this time. Remember, the order of an induction proof doesn't matter as long as you covered the step itself and the base case in the end. The induction step revolves around f2 times n plus 1. It should be the same as fn plus 1 squared plus fn squared in the end. We start by using the definition of the Fibonacci numbers, but we will want to use it more than once. The statement, and therefore the induction assumption, is about even indices of Fibonacci numbers. So we want to force even indices into our expression. We use the definition for 2n plus 1 to get this. Now, a trick that's often handy with Fibonacci numbers, we know that f2n can be written like this. But we don't use it to replace f2n, but f2n minus 1. This gives us an expression with only even indices. And this is where we will use the assumption. But here's the catch. We want to use the assumption in both places. We are in the induction step, where we wish to check the statement for n plus 1. Usually, we only use the statement about n to achieve this. Now, we intend to use the statement about n minus 1 too. This is allowed, but only if we check the first two numbers in the base case later. If we are using several previous steps in the induction proof, you have to show just as many in the base case. If we plug in the statements about n and n minus 1 and expand, we will get this expression here. We can do a similar trick as before and replace fn minus 2 by fn minus fn minus 1. Then it's just a few lines of tedious algebra, mostly the binomial theorem, that brings us to the expression we want. Pause here and check the calculation if you want, but there's nothing interesting going on anymore. And remember that you can start at the final expression and work your way backwards to an intermediate result, which might be easier. To finish the proof, we must not forget the base case. As already mentioned, since we're using the statements about the two previous numbers in the induction step, we must check at least the first two numbers by hand. But that is easy enough here. We simply calculate all Fibonacci numbers involved and check the square identities we need. Then, the inductive argument is the following. We have proven the statement for n equal 1 and n equal 2 directly. The induction step uses the two previous numbers. That allows us to go to 3 using 1 and 2. We can then go to 4 using 2 and 3, then to 5, to 6, etc. This is not something you necessarily encounter right away with learning induction, but it is a very common form of induction when using it later on. To wrap up the video, let's prove this Fibonacci identity without induction. Well, at the start of the section, I said that induction and recursion are more or less the same thing, but I'll try to get as close as possible to a non-induction proof. One very common approach to statements about Fibonacci numbers are tilings. Take a line of tiles that is n units long. We can cover it with tiles that are 1 and 2 units long. How many ways are there to achieve this? I claim there are exactly fn many ways. Let's call the number of tilings of a strip of length n Tn and analyze it. For some small examples, we can simply list all tilings. In particular, it works for a strip of length 0, which we can tile in exactly one way, namely not at all. A weird edge case, so you might want to meditate on that a bit. And for a general strip of length n, any tiling will end in either a 1 tile or a 2 tile. That leaves a shorter strip in front of it, of length n-1 and n-2 respectively. So the number of ways to tile the whole is the number of ways to tile these shorter ones. And since they are complementary cases, we can add the numbers. We now have the same starting numbers and the same recursion rule as for Fibonacci numbers, so these must be Fibonacci numbers. And with that, we can write down a super simple proof for the identity we are interested in. Take a strip of length 2n. There are f2n many ways to tile it. Now look at the center. The gap right in the middle is covered by a 2 tile or not. In the first case, the parts before and after are of length n-1. Both can be tiled in fn-1 ways, and since these are independent, we multiply them. In the second case, we have 2 halves of length n. With the same argument, we get fn squared ways to tile that. We sum these cases together and that's it. That's what we wanted to prove. The f2n ways to tile this 2n strip can be decomposed in these two cases. Now, it is pretty much impossible to think of this proof if you've never heard of the tiling idea. But once you know about it, the proof itself is a piece of cake. As I mentioned previously, one could argue that this tiling proof itself is a form of induction, but in the end, the tiling proof is surely the one you will be able to remember and reproduce more easily. And with the tilings in mind, it is more intuitive why this is a statement about even index Fibonacci numbers, because then we can split right in the middle. And the induction proof, if you go back, it was more about clever use and manipulation of the Fibonacci definition than actually doing an induction argument. But while tilings are probably the nicer approach to Fibonacci identities in general, please do practice the induction proofs too. Coming to an end here, I hope you understood a bit how different types of induction proofs can be tackled and that you are well equipped to tackle other problems. More importantly, I hope you believe me that looking for other proofs is a worthwhile endeavor and that no single proof technique is the be-all end-all. There's still much more to say about induction itself, of course. For example, for n non-negative numbers we have this identity. You can prove it via induction, but with a very non-standard structure. First, you prove it for 2. Second, you show that if you know the statement for one power of 2, it also holds for the next power of 2. Lastly, you prove that if the statement is true for one number, it is also true for the previous number. This is appropriately called non-standard induction. Even though it looks confusing, it still allows us to reach all possible numbers. And learning how to write down ordinary induction proofs is crucial to be able to route down this heinous structure. So even if you find the induction exercises you have to do boring, please take them serious. But also challenge yourself by looking for other proofs. Both together will make you a much better mathematician. With that, thank you for watching and until next time.